So now let's look at how we approach free body diagrams for circular motion. And honestly, it's the exact same as you would do free body diagrams for anything else. But the key part is when you do the free body diagrams for circular motion, you're always doing the same forces. You just have to realize what kind of you have to identify what kind of acceleration that you're feeling at any moment in time. Okay, so let's take a look at an example. Suppose I am swinging. Let's talk about this where there's a I don't know if you've ever seen this carnival ride, but you're kind of like being spun in a circle at an angle. So like you're sitting here on a chair and it's spinning in a circle like this. And it goes faster and faster and faster, all right? And the question might be, let's just draw the free body diagram. Let's try to understand the motion, this circular motion. Like, why is there an angle here, and why, like, what are all the forces and how they're going to be related to each other? Okay. So you're moving at a constant speed. That makes it uniform circular motion. And let's draw the free body diagram. The tricky thing about these free body diagrams is there's a lot of three-dimensional aspect to it, because this circle is sort of like in the plane coming in and out of the screen, if you will. Right? It's not up or down. So this is, let's imagine that it's traveling like this. This is the front side, and then it's going around back like that. Right? That's my circular motion. So let's draw my free body diagram. I have gravity going downward. I have tension pulling this way because it's connected to a string. Anything else touching? Anything else feeling that force? No, that's it. Those are the only forces. The same forces we've been doing the entire time are the same forces that we have now. Okay, so we don't have any difference in the forces at this point. Okay. So let's look at, let's say we know this angle for some reason. We know this angle here. We'll call this angle theta. And I want to know something about, what are the net forces? As you can see, this net force is not going to be zero because there's no way these two vectors can add up. So let's split our vectors into the horizontal and vertical components. Well, I have, my tension really has a vertical component and a horizontal component here. And if this angle's theta, this angle here is theta. So that makes this part t cosine theta because it's the adjacent side, and this side here t sine theta. Okay, so the first thing we want to look at is the y direction. What is the net force in the y direction? And let's establish directions. We'll say up is positive, and we'll say to the right is positive at this point. Doesn't really matter, but yeah. So the net force in the vertical direction is going to be t cosine theta. That's in the upward direction, so it's positive, and mg is down. Minus mg is equal to the mass of this object times the acceleration in the y direction. Now let's think about the motion. Is it accelerating in the vertical direction? No, because it's staying in a circle like this, like in a horizontal circle, right? It's not going up or down or accelerating up or down, so the vertical acceleration is 0. So that tells me that t cosine theta must equal mg. Okay, that's our first relationship. Let's look at the x direction. F equals ma. Well, the horizontal force is t sine theta. And that's the only horizontal component force I have, just positive t sine theta, because it's to the right. It's equal to ma. And the a, now, it's clearly non-zero, so we clearly have acceleration. What kind of acceleration would be directed horizontally? In this case, from this point towards the center of the circle, that would be centripetal acceleration, which is equal to mv squared over r, where r would be the radius of this circle. Let me mark the radius of the circle here as r. Okay? So that's the relationship we have. So if you wanted to, say, calculate, say, the speed that you must be going to make this angle, right, then we can look at these two equations. We can say, well, I have my two equations are t sine theta is equal to mv squared over r, and t cosine theta equals mg. I can divide these two equations, t sine theta over t cosine theta is equal to mv squared over r divided by mg the m's are going to cancel, and this is going to be v squared over rg. And so the t's here cancel. Sine over cosine would have tangent of theta would equal v squared over rg. Okay? And so that would tell you that the faster, as I increase the velocity, the angle is going to change. The angle depends on how fast I'm moving, or my speed that I'm moving is. Okay? So that's it. Now, I want to talk about t sine theta here, this sort of what is causing centripetal acceleration. Sometimes you'll see this term. The cause of centripetal acceleration we refer to sometimes, which I don't like, but we will refer to it that way. That's just, we call it the centripetal force. Now, this is really important you recognize, this is not a new force. Okay, that's important to remember. This is not a new force. It is not a new force that you draw on the free body diagram. The centripetal force is just simply the force that is causing the centripetal acceleration, but it is one of the existing forces we already have. In this case, what's causing the centripetal acceleration, in this case, is what is the centripetal force that's causing the centripetal acceleration? It is the horizontal component of tension in this example. But it is not the only force. It is lots of forces. Any of the forces, normal force, gravitational force, frictional force, all of them can be centripetal forces. So the centripetal force is not another force you add to your free body diagram. I can't emphasize that enough. It's a very, very common mistake people make, is that they will draw the centripetal force as though it were a new force to add to a free body diagram, and that isn't correct. Okay, let's look at another example where a car is going over, or like sometimes we see this as a roller coaster problem, or sometimes we're just driving over a hill or something like that. Okay, actually, let's do a roller coaster problem. It's going to be a roller coaster. It's going to go down, and then you're going to do this little loop here. Okay, and you have this loop at the top here. And the question is okay, I have a car, I have a roller coaster, it's going to roll down, it's going to flip over upside down. And the question might be something related to like this circular motion. This path that it takes here is kind of circular in a way. It has some radius, it has some circular motion. Okay. Now let's draw the free body diagram at the very top here. And let's think about all the forces that are acting on it. We have mg going down, because gravity is always going towards the center of the earth, which is straight down in my pictures. Now, some people might think, oh, the normal force must be up. But remember, what is the rule of normal force? The normal force is a pushing force that is perpendicular to the surface. The surface is here, so the normal force actually has to be down. So that's the normal force there. So both the normal force and the gravitational force are that way. And you might ask, that seems like it should just fall. No, it doesn't necessarily mean it falls. That net force is going to be the centripetal force, right? And it's going to cause, you're right, it could cause acceleration. If my velocity were 0 here and I stopped, I would just fall down. But I'm going to keep going, and so this force changes the direction of the velocity. It doesn't cause me to just fall straight down. If my velocity up here were 0, then yes, I would just fall straight down. So we say the net force in the vertical direction is going to be Fn plus mg. Now I want to keep in mind, like, why did I make down positive? How could I make down negative? No, when you use centripetal acceleration, the positive direction always has to be towards the center of the circle when you're doing the forces. Because when I do the centripetal acceleration as v squared over r, this assumes it's positive. So the direction of, because v squared is positive and r is positive, r is radius. So this is assumed to be positive. That means I have to set my net force in the same direction that centripetal acceleration is going to be. or positive in the same direction. In this case, centripetal acceleration is this way because it's moving in a circle like this, and it's always the centripetal acceleration is directed towards the center of the circle of motion. So I have Fn plus mg is equal to ma, where a is centripetal acceleration. So my normal force plus mg is equal to mv squared over r. That means my normal force would be mv squared over r minus mg. Okay, and note that this normal force, see, this is where normal force is not always equal to mg. It really depends on the circumstances. So you can't just assume anything about normal forces when you're doing certain problems. You have to draw the free body diagram, and you have to work out the math about what we know, what we don't know.